Hi there, and welcome to the lecture video for section 2.6 on the topic of linear transformations. In this video, we're going to explore what was it in the last section about matrix transformations that made them so special to us. Why did we spend so much time focusing on those matrix transformations? And just to remind you, a matrix transformation was just one that could be expressed as multiplication on the input by some fixed matrix A. So let's jump in here and see what was it about those that we cared so much about. Let's start by defining a linear transformation, something that we didn't really define last time in 2.5. So here's our definition. Given any vectors u and v and Rn and any scalar c, the transformation t taking Rn to Rm, so this is a different dimension for our domain and codomain. A transformation taking Rn to Rm is called a linear transformation if the following two properties hold. T of the sum u plus v equals T of u plus T of v. So it's like this transformation can be split up and applied to both pieces of the sum individually. Then you can add the results. In other words, we would say the linear transformation preserves addition. And it needs to preserve scalar multiplication in the sense that T of a scalar multiple of u is really just a scalar multiple of T of u. So instead of applying the scalar to the vector inside, you can take the scalar outside and apply the transformation, then tack on the scalar at the end. So this is what we mean by a linear transformation, and we'll see why these transformations that are linear are very useful in a lot of ways. Anyway, the linear transformations preserve addition and scalar multiplication in the sense described here by these two requirements. So here's what why we really studied matrix transformations. It turns out every matrix transformation is a linear transformation. And that's just because if I wrote down a matrix transformation, T, applied to some sum, u plus v for some vectors u and v, if T is a matrix transformation, we know that can just be written as A times that same sum. Matrix A times that same sum. But remember, a matrix does distribute across a sum of matrices it's multiplying on, or column matrices it's multiplying on. So A times U plus V, just by matrix multiplication rules, is always AU plus AV. But AU plus AV, that's T of U plus T of V, right? AU, that's the matrix applied to U. That's the same as applying the transformation to U. AV is just the matrix multiplying V. That's the same as applying the transformation to V. So we've seen that T of U plus V does in fact equal T of U plus T of V, so long as our transformation is a matrix transformation. Similar, you can take a scalar multiple of U and say that's the same as multiplying the scalar multiple times A. But we know a scalar, when doing this matrix multiplication, can come out to the front, leaving just the AU isolated here. So that's C times the transformation applied to U. AU is T of U. So what we've seen then, since now we know that every matrix transformation is linear, what we've really seen is that dilations, contractions, reflections, and rotations, some of these that we talked about last time, are linear transformations. They preserve addition and scalar multiplication. We also saw that translations and affine transformations are not linear. Right? We saw those are two examples of non-matrix transformations, so they also can't be linear. All right, so let's play with a couple of examples here. Let's show that the transformation T of xy, defined by taking the input in R2, the xy in R2, back to R2 as 2x plus y in the first component and negative 2y in the second component. Let's show that this is linear. So all we have to do is apply this transformation to two arbitrary elements, x1, y1, and x2, y2 added together. Right? That's like our u plus v here. These are two arbitrary elements in R2. We're adding them together, then applying the transformation to the sum. Well, so let's see what this gives us. The sum of those two vectors I can compute. Easy to add two vectors. And now I can apply this transformation I'm not even looking at it through the lens of matrices, right? If you could show this as a matrix transformation right away, that would say it's linear. Maybe we do that next. But for now, I'm just going to go through this process here, just directly showing that it preserves addition and scalar multiplication. So what do I get when I apply t to this vector x1 plus x2, y1 plus y2? Well, I get in the first component 2 times what was in the first component of the input, plus what was in the second component, and negative 2 times what was in the second component goes back into the second component. So this is what we're left with. But notice I can break this up pretty freely. I could rewrite this as 2x1 plus y1 and negative 2y1 plus 2x2 plus y2 and negative 2y2. And what do we have here? This is exactly what we would get if we just applied t to that first input, x1 plus y1. So this is t of x1, y1. I shouldn't say x1 plus y1, it's just x1, y1. And this guy is exactly what we'd get if we applied t to x2, y2. So we've seen, yeah, t of the sum is the sum of the two images, right? The image of the sum is the sum of the two images. So this thing does preserve addition. I should say t preserves addition. Likewise, if I take a scalar multiple of any element x, y in the domain, this would just say I really have t times cx, cy, that's the scalar multiple. But this is just, again, following the definition of t. It takes 2 times what's in the first component plus what's in the second component. That goes back to the first component now. And in the last component of the output, we get negative 2 times what was in the second component. Negative 2cy. So what is this? Notice I can factor the c out of here and out of here. Bring that outside. And I have got exactly c times the image of xy under t. So this is preserving scalar multiplication as well. T of the scalar, the image of the scalar multiple is the scalar multiple of the image. So this preserves addition. Okay. Okay. So this is what we mean here when we say check that it's linear, right? Check that it preserves addition and preserves, not addition again, scalar multiplication. Now, what was the quicker way probably to show that this is linear? Notice I could write this as 2, 1, 0, negative 2 times xy. You can check that this matrix representation does work, but that shows that t is really a matrix transformation, which implies that it's linear already. So that would have checked us off that this is linear in one really quick step. Showing that t preserves addition and preserves scalar multiplication is an important thing to be able to do, but in this case, maybe there was a shortcut we could have taken as well. For part B here, let's show that t taking R3 to R2, so different codomain and domain, is not linear. But let's let t equal this transformation defined by t of x, y, z, t applied to an element of R3, gives back an element of R2 that is the square root of x, the square root of the first component from your input, goes into the first component of the output, and z, the last component of your input, goes into the last component of your output. Notice the y value kind of just disappeared here. Is that a problem? Who knows? But I think we can show that this is not linear. How do we do this? Same way as before. Since we're showing it's not linear, it would be kind of tricky, I guess, to show that it definitely could not be written as a matrix transformation. It's easier in this case to show that it either doesn't preserve addition or doesn't preserve scalar multiplication. I'll start with addition, see if we can break the linearity just using that. So I take two elements in the domain, two elements in R3 here, and I'm taking the transformation and applying it to the sum of those two generic elements. So what I'm really applying t to, this sum, is really x1 plus x2, y1 plus y2, and z1 plus z2. Now, what is this? This is, according to our definition here, square root of what sits in the first component of the input, followed by what sits in the last component of the input. Now, is this equal to t of x1, y1, z1 plus t of x2, y2, z2? Right? We're asking, is this equal? Well, you can figure out what this side equals. This is really x1 in a root followed by z1 plus, make some space for myself here, x2 inside the root, z2. And when you add these, see what you get. This is your result. So let's ask, oops, where did I make a mistake? I made a mistake right here. Z1 plus Z2 should have gone here, right? Last element of the input, last component of the input is the last element of the output. I should have had a Z1 plus Z2 here. Sorry about that. So then we're asking, is this equal to this? Well, the second components are fine, but certainly this sum of two roots is not the root of the sum, right? This square root operation is not a linear operation on its own. So the transformation applied to a sum does not equal the sum of the individual transformations. Does not equal. Not equal. That means t is not linear in this case. Does not preserve addition. And you can test it out maybe on your own, see if you think t preserves scalar multiplication. Give that a shot, see what you find out. But we already showed t is not a linear transformation. So let's talk a little bit more about these linear transformations. Let's talk about matrix representations of linear transformations. Well, given a linear transformation, t taking Rn to Rm, potentially different dimension of domain and codomain, the matrix A, which is m by n, which describes t, is the result of applying t to each column of the identity In. This is a wildly useful idea here. All we're saying is to find the columns of A, the matrix representation of your linear transformation, just apply t to each standard basis vector in your domain. Right, and here's a little explanation of why this works. To really see why this works, consider any vector u in this domain. So I'll just say its components are C1, C2 through Cn. Right, this is in the domain of t. Then we can write u as really just c times the first standard basis vector. Right, to be clear, the standard basis vectors are the standard basis vectors you might be aware of. E1, if I'm like in R3, for example, E1 is just the vector 1, 0, 0. E2 is the vector 0, 1, 0, and E3, 0, 0, 1. That's the standard basis vector. So certainly we could break this guy up and do C1 times that first guy, because that's in the first component, and you only have a 1 in the first component with E1, plus C2 times the second guy, because C2 is in the second component, and if you multiply C2 on E2, you only have a 1 in the second component, so it only puts a C2 in the second component, and so on, right? Add all these up and you'll get this C1, C2 through Cn vector. So this is really the value here, is that we're able, excuse me, to write this vector, no matter what input it is, we can write it as a linear combination of those standard basis vectors for Rn. And I've described those again here, maybe more generally. Then by linearity, we get a big result. Applying the transformation to U is the same as applying it to this linear combination of those standard basis vectors. And what do we really have here? Well, by linearity, we know we can break apart the sum into a sum of the individual images. Just like this. And we can go a step further. We know that a scalar multiple of a vector under this transformation can have that scalar multiple come outside. And so on, all the way out to the last one out here, Cn times T of En. And so what are we really left with here? We are left with, no matter what vector we had, this is really just C1 times the effect of T on the first of those standard basis vectors. Yeah, let's write it just like that. Let's see. And I suppose here's the big leap that we're going to take. We can rewrite it here as a matrix containing just those columns. T applied to E1 is the first column. Right? That's a column of a matrix. T applied to E2 as the next column, and so on, all the way out to the last column. We can write this previous line as just this matrix whose columns are made up of T applied to the first standard basis vector, T applied to the second standard basis vector, and so on. Set up that matrix and just multiply it with matrix multiplication by this column of those C values. Right, and remember, T takes Rn to Rm. So these images of T of the image of each standard basis vector under T is a vector in Rm. So each of these columns is m by 1 columns. And you have n of those. So put it together, this matrix here is m by n in dimension. That matches up to multiply with this n by 1 column here to make a result that is still m by 1. It's still in the correct codomain. Right? So what have we really shown? We showed that applying T to this vector U is the same as multiplying this matrix whose columns are made out of the images of the standard basis vectors under T. Just apply that to this column matrix that is really just the components of U. I made a mess of U up here, right? This is U. Write that guy as a column, and you have this. This is A times U. So the transformation of T on U, I'd say the transformation of U under T, is the same as multiplying U by this matrix A, where a matrix A is really just made of the image of the standard basis vectors put into the columns to make A. In this case, when we do this way, the matrix A is called the standard matrix of T. And notice this is similar to using elementary matrices to perform elementary row operations, right? We understood with row operations how to actually perform these operations on an augmented matrix. We didn't have a really good systematic way of describing that mathematically, right? Until we had elementary matrices, which would then be representing these row operations just as simple matrix multiplication. It's the same idea here now, but now our transformations aren't necessarily elementary. Now, whatever our transformation is, if it's linear, we know we can describe it as just matrix multiplication, just like we were able to do with the row ops using elementary matrices. So just to see what the value of this little statement is up here that we just kind of went through a proof of, let's see what this is really getting at. If I have a linear transformation, I know it's linear, then I can come up with the matrix representation of that transformation just by applying that transformation to each standard basis vector in the domain of your transformation, right? That's this matrix A that we built. So this is a great fact for us. It makes things super easy. If I want to find the standard matrix for this guy, I'm assuming it's linear. You could prove whether it's linear or not. We saw how to do that. But if it's linear, we know all that we have to do to come up with A, the matrix representation of T, is apply this transformation to both of these standard basis vectors in R2, right? Because this transformation T takes R2 back to R2. Takes R2 back to R2. So what does A do to the standard basis vectors of R2? To be clear, those basis vectors are 1, 0, and 0, 1. Easy in R2. What do we get here? This is T of 1, 0. That makes the first column. And T of 0, 1 makes the second column. This should be easy, right? T of 1, 0, x equals 1, y equals 0. Just use this formula to figure out what it is. 1, 0 gives you 1, negative 1. So that's the first column of our representative standard matrix. T of 0, 1 says x is 0, y is 1, we get 1, 1. Just by plugging into here. Right? And that does it. That gives us our standard matrix. T of xy is the same as multiplying by 1, 1, negative 1, 1 on xy. And this one probably wouldn't have been too bad to figure out without this method of applying the transformation to the standard basis vectors of the domain. But if you had a more complicated transformation, maybe in like 3 variables and they're all mixed up in strange ways, or 4 or 5 variables, and they weren't in a very specific order, you have x's and y's and z's all in different orders. So long as you knew that it was still linear, it's easy to write down this standard matrix just by applying it to these very simple basis vectors. 1, 0s, 0, 1, then zeros, 0, 0, 1, then zeros. Since these guys have such an easy, simple form, it's easy to apply and find these columns, no matter how complicated the linear transformation looks. Okay, so hopefully that makes a connection between this section and the last one in terms of why do we care about these matrix transformations? It turns out those are the ones that are linear, and linear transformations, well, look like matrix multiplication certainly can always be written in that form, but we'll see they have nice properties that allow us to take this idea a little bit further in future sections. Something about that linearity of a transformation gives us a lot of ability to work with it in linear algebra, because it looks like matrix multiplication. We've studied how these things come in handy, solving systems and other uses. So maybe it's not a big leap to see why that linear transformation, ability to write it as a matrix multiplication, might come in useful. Okay, That's it for this section. Quick video today on this one. Thanks for your attention.